Hello, welcome everybody to our session about vSphere Resource Deep Dive. We want to talk to you about the following things. So Frank is going to cover some compute and storage points. And then I will be taking over and talk about network some more. And we try to have some time left for some questions at the end of the session. So let's start off with a quick introduction from our side. I'm Niels Hagoort, which is a pretty Dutch name. I mostly get Niels or Neil. That's okay. I'm an independent architect, VCDX, vExpert, NSX as of last month, I believe, and blogger at cloudfix.nl. Frank?
Yeah, thanks. So my name is Frank Denneman. When we were preparing this slide deck, I was enjoying the summer of 2016. But since today, I'm actually back at VMware, and I'm going to focus on some cool new projects. Cool. So let's talk about compute. So I've been writing the NUMA deep dive. I'm now in part 5, I believe. And I already wrote more than 15,000 words. I've got 25 minutes, so let's go. So back when I was at pNIC Data, I was working on a big data project, and I had access to over 90,000 servers, 90,000 hosts. And so one of the things that I did was to look at how does the architecture of the host look like. So I discovered that 85% of all the hosts were dual socket. So by raise of hands, how many of you are using dual socket servers or are going to dual socket servers? Yeah, like the most, right? Okay, cool. So with that data point, I started to look at the memory configuration. And what I noticed was there's a lot of 256 gig servers, 512, but also a lot of 384 gig servers. And that's an interesting thing, because when you look at today's architecture, that's a NUMA architecture, and that NUMA architecture that has a couple of focus points. So NUMA stands for non-uniform memory access. And what does that actually mean? So if you look at the diagram, so you have one CPU, and on that CPU there's the integrated memory controller. And attached to that memory controller are 4 channels. That's considered to be local memory. Now, between the 2 CPUs, there's a QPI. That means Quick Path Interconnect, and that's an interlink. That allows the CPU to actually access memory that is attached to the other CPU. So when you have a workload that's running, in this case, on CPU 0, if it stores data in the memory attached to that CPU, it's considered local access. But once it stores memory or it accesses memory on the other CPU, that's considered remote access. That means that when it accesses memory that is connected to the other CPU, we have a different memory latency access. And that's the reason why you call it non-uniform, because the latency is not the same. The bandwidth is not the same. So there are some focus points on how to create a system that is persistently and consistently creating the same level of performance. So the 3 focus points I want to discuss today is the cache snooping modes, the DIMM configuration, and how to size accordingly. So let's talk about cache first. So let's go a little bit deeper in the rabbit hole and take a look at, hold on. The clicker is not working very well. This is a diagram of a CPU architecture of the Haswell, the latest CPU architecture. I'm going to build it up slowly, by the way. So the blue boxes are the cores. Those are the things that really do the compute. And each core has layer 1 or level 1 and level 2 cache. That is private. That they own that cache. But the whole architecture has a last level cache that is shared amongst all cores. Now that last level cache is called an inclusive cache. And what that means is that it has to contain all the data that is contained in the L1 and L2 caches of each core. So when a CPU modifies data, it's going to write it to their private cache. That means that the moment another CPU wants to access that same data, it needs to verify if that data is the most recent one. So to do that, it's going to snoop around the cache. So it's going to send out a request like, who has got the latest data of that memory? So in order to do that, you have to have these scalable rings. Those are basically the lines. That allows the traffic to move across all the cores. Now you can imagine that if core 1 wants to access or wants to have data, it has to send out a request, and all these cores need to figure out whether they have that data. And once somebody says, I have the data, it needs to be fetched. So it can happen that core 0 is going to access something on core 23. So it's going to enter its own ring, it's going to, through the buffer, back to the other ring, it's going to fetch it and go all the way back. That is also non-uniform, right? So one of the things that Intel did, and this is primarily Intel, it looked at a way that we want to contain all the broadcast within the CPU. Because the moment you start to provide more cores, you're going to see more traffic. So that's the reason why they created different type of snooping modes. So they started with an Nehalem architecture, and they said early snoop. That means that a particular core is going to ask every core whether he has that data. Now, that was like 2 or 4 cores. We're now today we have 22 cores already on a package. So that is a lot of noise. So the most recent one is called home snoop with directory and opportunistic snoop broadcast. That's the most left one. And you can see that the performance is the latency is low and the memory bandwidth is high. So what happens, let's turn back, is that a CPU will ask not every core, but the home agent connected to the memory controller, saying, hey, can you figure out which core has the data? And he has a little directory to figure that out. But if the overall utilization of the CPU package is low, it's going to say, no, I'm not going to wait for my home agent. I'm going to opportunistically broadcast my request. So that is the most interesting one today. The reason why I'm telling you this is that there are some vendors that actually forgot to optimize for this behavior. So some servers actually run with early snoop. Now that's the last thing you want to do when you have multiple cores in your system. One of the things that it does not only look in its own CPU, in its own package, it also goes to the QPI, to the other CPU as well, creating another broadcast storm. So that's one of the most easiest way to optimize your system nowadays. Look at your server vendor documentation and see what they have. Go to your test environment, boot one server into the BIOS and go check it out, right? Now there's another mode, which I think is kind of interesting, and that is COD. That stands for cluster on die. So let's take one step back. So there are multiple core configurations. There's a low core configuration, a medium core, and a high core. So what does that mean? Let me see if this works. No. So a low core count configuration contains up to 10 cores. So what you have is you have the left side. There is no right side. So you only have one ring but it also means you only have one controller. With one controller, that controller needs to access 4 memory channels. So a low core count will have a reduced amount of memory bandwidth compared to a medium core count and a high core count. So if you're considering between 10 or 12 cores to equip your service, I would recommend you to go to 12, because that's a medium core count. So a medium core count is you have the left side, and then you have one part of the right side. And it contains the amount of cores that you are ordering, right? So with that, you have 2 memory controllers. So there are 2 channels on one memory controller, 2 channels on the other, more bandwidth. So think about that. Just 2 cores will give you more memory bandwidth. And then you have the high core count, and that means basically this. So one of the things what you can do with medium core count and high core count is you can do a cluster on die. And that is particularly interesting for highly NUMA optimized workloads. So what you do with cluster on die is you're going to separate the 2 rings, and you're going to create 2 different NUMA domains for the cache. So that means that these cores and that those caches are a part of one NUMA domain. So they're going to look for that memory in that NUMA domain. That has some impact on your VM sizing, but also on your memory configuration as well. I would recommend you to look into that if you have those type of workloads. Don't do it if you're running all across the board workloads, because that will only provide you headaches due to the sizing, right? So let's talk about DIMM configuration, and specifically why 384 is not an optimal configuration. So what you have in this diagram, you have 2 NUMA nodes, and each NUMA node has a memory controller, 4 channels. So if we put 4 DIMM modules on each channel, you create a region. And within that region, you're going to interleave memory throughout that region. So you're going to use the entire bandwidth of all 4 channels. That is the most optimal to get the most optimal configuration to get the best bandwidth. Now, if you take 16 gig modules, which is the most popular one nowadays, and you want to make 384 gig configuration, you're getting this. Now, the interesting part is that although you're buying 2400 megahertz DIMMs, you're not getting that bandwidth performance. And that has something to do with the amount of ranks, and a rank is a number of DIMM chips per channel. If it detects a number of DIMM channels or a couple of ranks, that is going to impact the electrical charge or the actual load on the channel itself. Because it's that much, it has to down throttle the bandwidth to keep up with all the electrical load. So what you're getting with the 384 configuration in this end, you're getting 1866 megahertz of performance while you actually paid for 2400. That is not the best thing to go forward, right? So I looked up the most popular server vendors, and this is basically what they're saying. If you buy 2400, you're getting 1866. That's a 28% performance drop, right? Now, you can also buy LR DIMMs, and LR DIMM stands for load reduced, and what it does, it has a buffer on the DIMM module that basically abstracts the amount of ranks. That allows most server vendors to actually bump up the memory bandwidth. So you're getting a 12% drop. Think about that when you start to configure your server. Try to avoid a 3 DIMM per channel configuration. Because if you use 2 DPC, 2 DIMMs per channel, you can use the entire bandwidth of your memory module, right? So let's say you say, but I really want 384 because it totally aligns with the number of cores that I have, the number of megahertz that I have with my memory. If you want to do this, this is the best approach. Buy 32 gigs and 16 gigs and apply it like this. The bigger ones first, then the smaller ones. For me, that is a weird configuration because I want to keep everything the same. And you don't want to deal with which memory model do I need to buy. So I don't think this is the best recommendation I can give you. If you look at price, performance, I believe that this is the best one, 512, with 32 gig modules, with a medium to high core count CPU design. So you got 2 memory controllers per CPU socket, and you got quad channel, and you got the best performance of your memory modules. So now you got that in place. Now you need to figure out how to actually consume those resources. And if you look at ESX, it's the CPU scheduler that actually assigns the time of the core or the HT, the hyper-threading thread. It's the NUMA scheduler that actually does the initial placement and the load balancing. So your vCPU configuration will impact your initial placement and load balancing, and eventually it will impact CPU scheduling. So I made a diagram of the components. And in the lower part, you will see the physical layer. You see your NUMA node 0. You see your CPU packets, which is a fancy word for the CPU, basically with the pins, your memory. And on that CPU package, you have your cores and your threads. Now, if you look at the ESX layer, there's something what's called pCPU. And I think you all saw it in your ESX top. That P does not stand for physical. That is the ultimate abstraction layer of a physical resource. So a pCPU can actually absorb or utilize a complete core, or it can use a hyper-thread. You don't know that, right? But the interesting thing is, the NUMA scheduler actually counts the number of cores to figure out what the NUMA client is. And the NUMA client is the atomic unit of scheduling and load balancing. Sorry, initial placement and load balancing. Sorry. So what it does, if you create a 12 vCPU system on a 10-core node, it's going to count all the cores, 1, 2, 3, 4, 5, 6, 9, 10, and say, okay, I cannot place all my vCPUs inside one NUMA node, so I need to create 2. And what it does, it's going to split them or equally distribute them across those 2 NUMA nodes. So you'll see 6 CPUs, vCPUs on one NUMA node, and 6 on the other ones. It doesn't mean that those 6 are going to use a physical core. It can also use a thread or a core, because it's the CPU scheduler that decides whether you use it. And that depends on your progression, on your entitlement, and that means shares and reservations, right? And the amount of overall utilization in the host. This is an interesting thing, because vCPU 0 can still use the memory in the other NUMA node, because it only looks at CPU. It tries to allocate all the memory in the local node, but sometimes there is no room, so it has to take it from the other node. So it's really difficult to confine the memory to the CPU location. So in order to do that, I would say resize your vCPU to match the core count. So try to do from 12 to 10. But then we enter into a different realm, like political. I want 12 CPU because my vendor says so. Well, we all know that story. So one other thing that you can look at is actually use the advanced setting, vCPU NUMA prefer HT. That is a complicated name for count threads instead of cores. If you use that, I suggest you also look at cores per socket, but use it correctly. Align it with your physical topology of your CPU. So after our session, one of the performance engineers, who actually is responsible for the CPU scheduler, is going to talk about this in detail. So if you can stay, stay, because that's brilliant. So if you use NUMA Prefer HD, and this is, by the way, a VM level configuration, try to use cores per socket. Because what you can do is you can say, I want to have 12 vCPUs. I'm going to allow NUMA to count the threads instead of cores. So NUMA will say, okay, I can create a NUMA client with 12 cores on one system. Now, the next thing you do is use cores per socket, and you're going to say, this socket contains 12 cores. What vNUMA does is going to expose that to the operating system. And that's a real thing of beauty. Because what it does, it shows that all 12 vCPUs, starting from 0 to 11, are in socket 0, and it's one NUMA node. And this part, the logical processor to cache map, that is the interesting part. Because what it shows is that all cores use the same cache. Now, that means that your application and your operating system can use its optimization for cache to actually say, hey, if you want to have data, check the cache first instead of going to your memory controller. That will give you a lot of performance increase. So take a look at this when you start to right-size your virtual machines. So with that in mind, I'm talking about nanosecond optimizations. I'm talking about increasing the bandwidth. But the funny thing is, most people don't really think about how far the actual data is, because we're trying to grab it from cache, and if that's not possible, trying to grab it from local memory. If that's not possible, from remote memory. And if that's not possible, we need to go to storage. So how far away is your data? So when it's in the CPU register, basically the moment it's being processed, it takes one cycle. So to give you an analogy, I'm using the operands 1 plus 1, right? Now, if I'm going to process 1 plus 1 in my brain, that's similar to a CPU cycle. If these operands are in the L1 and L3 cache in your processor, that will take roughly 10 CPU cycles for the CPU to get it. In real life equivalent, that means I have to walk through to that door, get 1 plus 1, go back, tell you it's 2. Now, if we do the same with local memory, that's 100 CPU cycles. For me, I need to go all the way down to the entrance of this building, grab 1 plus 1, come back, say it's 2. Now, if I do it on disk, I need to go to New York to do this, right? So why are we still doing this to ourselves? Why are we still going all the way down the stack? This diagram is courtesy of Chad Sackett of EMC, by the way. And you can see that every single level is basically a hop, means CPU cycles, means latency. So you need to reduce this. And one of the things how you can reduce it is to create local storage, right? Go look at the flash technology nowadays that you can implement in your own server. So flash by itself is cool, but what we saw, if you put flash behind a traditional adapter, you're going to have a bad time, because the bandwidth of your flash completely exceeds what the controller is actually designed for. But also the software. Software is very important nowadays. What we see, and what I saw when I worked with pNIC data, is that at this point, software, badly written software, is actually the bottleneck nowadays. Because most software is written for a disk, right? So what they did was the NVMe, the group for the NVMe, they architected the entire stack for using this type of speed. One of the cool things is that they're using an I/O queue per core. Compared to the old days, there was one I/O queue on the core for each workload. So you have to go to that particular core, go back. That's a thing of the past with NVMe. So every core can execute its I/O queue. Another thing is that the driver stack is reduced with the number of steps. So compare that to the entire storage stack. Now you have this inside your host. The old driver stack typically took 27,000 I/O cycles, or 27,000 CPU cycles to process one I/O. The NVMe takes 10,000. That is a lot of savings. You can use that savings to actually do other stuff with your CPU. Now, not all drivers are created equally. So the inbox driver, meaning the default driver that comes with ESX, is equipped to do a lot of NVMe devices. So what I did was I used, with a P3700 from Intel, I used the inbox driver, and then I loaded the async driver, that is the driver of Intel itself, and I compared the latency. Left part, inbox, right part is latency. Same workload, same system, everything is same, just by changing your driver. So think about that, research that as well, right? And with that, I'm going to hand it over to my good friend, Niels.
Thanks. So let's talk about network and some of the host-related stuff going on for network. It's becoming an increasingly important fundamental, right, in your virtual data center, with nowadays products like, hyperconvergence, software-defined networking, software-defined storage, and workloads that are actually requiring a lot of network I/O. Think about network functions virtualization and applications like that. So I want to highlight some of the things that I find interesting about host configuration with regards to networking. So let's first talk about physical NIC considerations for VXLAN. And VXLAN, of course, because VMware's offering on software-defined networking is NSX, which uses VXLAN. And when you look at that, you'll see that VXLAN is creating an additional layer of packet processing. You'll need to encapsulate packet, decapsulate packet, and that takes CPU cycles, right? So that's why you want VXLAN offloading. You do not want your CPU to be bothered with the extra cycles for that encapsulation and decapsulation. VX offloading will help with that, and it will help because the TCP, your legacy offloading mechanisms will not always apply to VXLAN, because VXLAN is packet within a UDP packet, right? So VXLANing helps. And looking at the Intel offering of some of the network cards available, your physical NICs, I highlighted some of the stuff that I find interesting. So typically, you're looking for form factor. Which form factor do you use within a host, and bandwidth. But nowadays, it's, because of VLAN, important to see if a NIC actually supports VXLAN offload, right? When you're looking into NSX or another software-defined networking solution. Next to VXLAN, I highlighted some other features, including Intel's VMDQ, which is the virtual device queues, and RSS, receive-side scaling. But first, let's focus on VXLAN. So once you actually have made up your mind about a specific network card, physical NIC within your host, you want to be able to check if VXLAN is, even though it's hardware supported, if your driver stack also supports it, right? So you will be able to do so using, in example, ESX CLI to list your network adapters. And in that, you will see the driver module used for your physical NIC. Using the ETH tool command, you'll be able to check the version you actually are using for that driver module. And that information will allow you to look up the specifics on the HCL from VMware, the hardware compatibility list. So in this case, I'm using a Broadcom 10 gig driver, so the BNX2X driver module. And you'll see that the HCL states that it's actually supported, right? So we're all good. But still, you want to be looking at the parameters and the configuration of that specific driver module. In this specific case, I thought it was interesting because it is supported hardware-wise, it is supported by the driver, but it is disabled by default in this specific case. So even though you're thinking you are using VXLAN offload, you're not. So enable it, if you will. In this specific case, the BNX2X driver, the inbox driver itself, it had some issues with it. I know Anthony Spiteri actually wrote a blog about it, and the thing was the inbox driver, the BNX2X inbox driver within vSphere, was causing some panics when VXLAN offload was enabled and running on high load. And that same knowledge base article and Anthony Spiteri's blog are directing to actually a async driver, so the vendor-specific driver. So keep in mind, always check the actual parameters and if features are actually enabled. The same goes for this one. Looking at the slide back, I'm using the vmk load mod command, and the same you'll be able to do with the ESXCLI command. But still, you'll see also here that the VXLAN offload mechanism is actually disabled. So, talking about the drivers, you always want to make sure that, as said, the physical NIC supports it, the driver supports it. If the driver module requires any configuration to enable or disable features. And keep in mind, and Frank said that about the NVMe, the storage driver, right? Always keep in mind that you'll look out for vendor-specific drivers because it can make a world of a difference, performance-wise but stability-wise, right? Some other configurations on your physical NIC. So this was the VXLAN offload part, but I found some other interesting thing. Talking about physical NIC considerations for VXLAN performance, I want to highlight these features. RSS, receive side scaling, and NetQueue. Both need hardware support from the physical NIC, where RSS is listed or not, and Intel VMDQ, as said, the device queues. That's the one that's actually used by the vSphere-baked NetQueue feature. And interestingly, NetQueue is mostly, well, most modern NICs support both. And where NetQueue is mostly enabled by default, it only uses MAC filters to determine the network I/O and which queue it is put into. Because in the end, both have basic functionalities, and that's creating multiple queues for receiving traffic on your physical NIC. RSS, on the other side, does the same, but it leverages more header information to actually balance the queues. So you're talking about IP, TCP used MAC addresses, where NetQueue only uses MAC. So looking at RSS for VXLAN, it's the most important difference between NetQueue and RSS, because NetQueue always only uses the MAC filters, is when you implement NSX, for example, you're using the VTAPs, right? The tunnel endpoints. So a single physical NIC with that host having a VTAP, it will always have the same MAC address, right? Same goes for the destination host within the same cluster. So when you have a network path between those, it will always traverse via the same queue. So you're constrained by the actual cycles your CPU has. So when enabling RSS, you'll see the diagram that you're actually using one core. And when you enable RSS, receive side scaling, you will be able to use multiple queues, thus multiple CPU cores. And that's what you really want, right? Because in your virtual data center, you don't want to be constrained by one core. You want the network I/O balance and the queue balance across all available cores. So RSS by itself also requires manual configuration. And again, looking at the driver modules, you'll need to actually unload a driver module. In this case, I used the Intel 10 gig, the EXGBE driver, and enabled it again with a specific set of parameters enabling RSS. And the good thing to know is that the load command and the actual configuration used depends on the used driver module. Even if it's the inbox driver or the async driver from the vendor itself. And to give you an idea on how this affects performance using VXLAN, I found this diagram, and it's in official VMware documentation actually. And it was a test using, I believe, some 16 VMs on a 10 gig network with RSS disabled and enabled, using different packet sizes. And what they noticed is that when receiving traffic, we're still talking about receiving traffic, that they weren't able to fully utilize the bandwidth of 10 gig. Only when they enabled RSS, receive side scaling, they were able to go up to 90–95% bandwidth. And again, hardware matters, right? So the actual component, the NIC and the chips that you are using also makes a huge difference in that performance, in those performance metrics. And when looking at, again, an Intel offering, so on the top you'll see a VXLAN frame with the actual Ethernet frame encapsulated within it. And I saw that the X500 series by Intel was able to do RSS, but it was able to scale RSS using the outer UDP information, where the actual, X700 series was able to decapsulate in an RSS process and use inner and outer header information to actually balance across multiple queues. So drivers do matter, and the used chipset do really matter for your NSX performance, right? So another thing I would like to talk to you about is the following. So, to give you context, we were at a customer, which is a large telecom company, and we were looking to implement some NFV applications on a virtual infrastructure. While doing so, we quickly came to the question, what is the actual performance of a distributed vSwitch, or vSwitch? Only to find out that that's the wrong question, right? There's no fixed metric for distributed vSwitch performance and throughput, or packets per second, or stuff like that. So the question is, how much CPU cycles can the vSphere kernel consume to actually do network I/O? And that's an interesting thing. Because looking at network I/O and the vSphere network stack, by default, a VM will have only one transmit thread, the so-called TX thread, and one receive thread, which is called the Netpoll thread. We just talked a bit about the RSS and NetQueue and how that fits in multiple queues. And each additional thread would deliver up to one core, actually, of additional performance. So put that in a diagram. It's not the nicest diagram, but from VMware official documentation, you will see on the top that you'll have the VM with the actual vNICs configured to it, and that's where the TX thread lives, the transmit thread. Well, you'll have the virtual switch kernel layer, and on the bottom you'll see the physical uplinks, right? And that's where the Netpoll thread lives. So we created a test, and to be clear, we are using NetQueue for this one because we were not using VXLAN by that time. And what we saw, we created a set of VMs. In this case, we had one VM running a packet generator, which was DPDK enabled. So there's a pull mode driver from Intel. And what we saw, we use that workload because it consumes every single vCPU it's entitled to. In this case, you'll see 4 vCPUs. And what we saw is that the sys metric, which is the metric used in ESXtop to show CPU utilization by the vSphere kernel, was up to 100%. In this case, I don't know if it's clear, it's 103 actually. So keep in mind we had NetQueue enabled. So what we saw using netstat is that NetQueue actually created multiple worldlets. So it was creating multiple threads using multiple cores, and by that able to receive more network I/O. And the same goes for TX threads. So again, where the last test I just showed you was the receiving side. This is the transmitting side on a different host. And what we saw there is again that the packet generator, it's polling, so it's consuming all its vCPUs. And again, the sys metric is up till 100%. And that makes sense because a VM, no matter how many VNICs you have configured to it, if it's 1 or 10, which is the maximum, it's always bound by 1 TX thread per VM. You have a network I/O intensive application like our NFV application or the packet generator in this case. You want to exceed the 100%. We're limited by 1 core. So you'll be able to do so on your VNIC, and it is required to use the VMXNet3 adapter. You'll be able to configure a separate TX thread per VNIC. Not necessarily for all VNICs. So this is an example of VNIC 2 of my VM. It's actually a VM using 2 VNICs now, and each VM has its own TX thread entitled to it. So when we ran the test again, we saw that the VM, again, uses all vCPUs it has entitled to it. But the sys metric was up to 200%. And again, that makes sense because we now added the specific extra TX thread. So that was interesting, right? And using netstats, again, we were able to see multiple, 2 cores, 2 worldlets in this case. So we verified that it actually was using 2 threads. Side note on this is that the sys metric, which is now running at 200%, it's accounted for within the VM. And that's interesting because in this specific project, we were using vCloud Director, and their blueprint stated that we had to use pay-as-you-go model. And what that does for you is it will set a limit and a reservation on the VM itself. But because of our workload already consuming all CPU it has entitled to it, and it has a limit set, in this case, to 100% of its entitled CPU resources, it wasn't able to utilize the full 200%, right? So with that all in mind, keep in mind that it's accounted for within the VM, and you do not want to use limits. Another thing that is interesting is that we saw that when the VM when the CPU schedule is able, we saw that the CPU threads used for network I/O were actually placed within the same NUMA node as the VM was running. So that was interesting to see also. And Frank talked about NUMA boundaries and how to configure those. So when you summarize all that information, it's good to know when you use network I/O intensive applications that you are able to scale, transmit, and receive threads, and by doing so, increasing network performance. But the extra CPU cycles, you'll have to take into account, right? When Frank told about right-sizing your VM and be able to match it to your physical topology, you'll also need to take into account the network I/O settings, or network I/O CPU cycles. So that already concludes our presentation. Are there any questions for me or Frank? No, this is strictly Ethernet. Oh, sorry. So the question is if it's applying to fiber channel networks as well. No, it's not. It's strictly Ethernet. So, yeah.
Any other?
No.
Sure. So to summarize the question, because of the diversity of the workloads, how will you do this? Do you take one workload and individually and start to analyze it? Or one of the things what we do is basically look at the noisy neighbors within your CPU, start there, and then offload. One of the things that I would always do is look at your CPU topology first, and then see which virtual machines are not a match, right? And then basically that's your first selection, and then go on deeper and deeper and deeper. Right? Yeah. Awesome.
Yeah, fair point. So RSS is actually, you were stating you were actually enable it. I was talking about RSE on the physical NIC, and fair point, you can enable RSS as well within guest, right? And that allows you to even have a better balancing, right? Good point. Well, from a vSphere, so the question is does it relate to a UCS environment as well, right? Because you have the fabric interconnects and it's just a slightly other topology. Well, this is from a vSphere kernel perspective. So yeah, same goes for UCS as well.
Well, so what are the optimal configurations, right? The optimal configurations is not to use a 3 DIMMs per channel configuration. That's the essence, right? That keeps you within the boundary of the memory bandwidth that you're actually buying, right? Okay. No. Or you can do that with load-reduced DIMMs, but then take a smaller hit. You see some vendors actually go to a 2 DIMM per channel configuration as a recommendation, and even not even allow it to actually say, hey, I want to give you the best performance. There's a lot of troubleshooting involved. And they say, yeah, this is the nature, but nobody really explained it thoroughly. Well, it's complex theory, right? So I actually wrote a memory deep dive on my blog. It's a 7-part series. So if you want to have a good night's sleep, go take that one. In the back. Sorry? Yeah. Yeah. Whenever I'm allowed by VMworld, right?
Otherwise, I will.
Yes. Any more? I need to look at my boss to actually see whether he allows me to do some work on it. But no, not putting you on the spot, that's true. But yeah, we're working feverishly on it, and we hope to, at least by the end of the year. It's seriously a lot of work. And like I said, I'm in the 5th part of my NUMA deep dive. It's already 15,000 words. I still need to do like 3 parts. He needs to do a lot of stuff as well. So yeah, but we also need to compress it, not like you have a Lord of the Rings type book, right? So, okay. One more and then we need to quit.
Was there any additional considerations taken with factor MS clustering sitting on top of virtualization? Any specific suggestions for configurations that makes them match better, also for heartbeating and everything else?
Sorry, come again. I don't understand your question. MS clustering sitting on top of virtualization. With regards to my network bit, you know, can't think of any actually. Sorry. If I do, I will let you know.
I know there's settings on the MS side to kind of lessen their requirements that have, you know, been pretty successful. I'm just trying to get drop a lot out.
Let's talk offline. I'm actually pretty interested in that.
Okay. Thank you all for coming.
Yeah, thanks.